All right, you can see that this section of course is 17.2 on galvanic cells, and then you can see from the learning outcomes you don't have to do a lot except be able to recognize the basic components in a galvanic cell. All right, so here's a diagram of a galvanic cell. Let me just walk you through what's happening here. I'm actually going to start over here, and I just want to explain. You've actually done something similar to this, where you put a metal in a solution that contains the ionic form of another metal, and you've had an electron transfer go on, right? So you did that with, you added zinc metal into copper 2+ ions, and the zinc metal gave up its electrons, and the copper 2+ ions picked them up, became Cu0, that is elemental copper, and then that precipitated, deposited itself on the outside of the zinc piece of zinc that you put in the solution. So in this case we've got something similar, but it's going to be copper and silver 1+ ions. Now obviously there has to be a counter ion to the Ag+, and you could imagine that counter ion, that is its negative counterpart, is something like nitrate ion NO3, and that's exactly what I'm going to use as the example here. So let me just get the pen. Okay, so in here then, in this solution here, what we've got is we've got AgNO3, but of course that AgNO3 is silver nitrate ion in solution. In other words, it's aqueous. Okay, there's my little wire of copper there, and then you put the copper in here and you start getting this blue solution here. So what's actually happening is, of course, this is actually Ag+. The copper's giving up electrons to that Ag+ there, like that. And of course, as the copper does that, it produces Cu2+, copper ion. Well, it's actually copper nitrate there, and copper nitrate solution is blue there. And of course, you get this precipitator silver, which is a little bit hard to see there, but you can clearly see the copper nitrate that's being produced as that blue solution. So why did I explain all that to you? Well, if you recall back earlier, I was talking about writing out half reactions for things. Now, they don't really exist per se, but really what's happening here is you've got copper gives copper 2+ plus 2 electrons, and you've got silver plus 1 electron gives silver metal. And whilst half reactions don't really exist in practice, you can kind of make them exist at least a little bit in practice. And the way you do that is you use a galvanic cell, which is what this thing is over here. So what's the important points and components in this galvanic cell? Well, you have a strip of copper metal there, right? So that's equivalent to this copper metal here, right? And over on this side, you've got Ag1+, right? So silver ions here, and of course the counter ions, which are NO3 1- nitrate ions here. And that's obviously the equivalent of these guys here. Now, the trick with the galvanic cell is basically to separate the flow of electrons via a wire. So what's happening here is this copper strip is still giving its electrons to Ag+, but it's giving them up through this wire here. So the electrons are moving in this direction, and they're then flowing down to meet Ag+ here. This is then reduced, of course, to silver metal, which is then being deposited on this thing here, which is an electrode. Okay, so that's the basic idea. You're in a sense, in practice, trying to create two half reactions. It's not really the case that they're half reactions, but it's pretty close to that. The reason why it's not really the case is there's also in here, where's my pen, there's also in here this thing called a salt bridge, and that's essentially making this solution here, right? And it's allowing this flow of counter ions. In other words, every time one of these silver ions gets converted to a silver metal atom, this counter ion can no longer stay here because there's an excess of negative charge in the in this beaker, and therefore it moves up through this salt bridge here. So over here, what's happening is as this copper is losing electrons, it's forming Cu2+, it now needs a counter ion, and there it is, NO3, 1-. So in that way you get this by having this salt bridge, you allow this flow of counter ions, which then means the system can work correctly, and in a sense it's like splitting the reaction up into two half reactions. Now, the nifty thing about this, of course, as you well know, is this is what a battery is, and a battery is essentially a bunch of galvanic cells put together, but this is, in a sense, the simplest kind of battery here. And of course, as electrons flow through here, they can do what's called electrical work, and you can actually use that to do things. Now, that difference in the ability of copper and silver to gain and lose electrons is actually measured as a voltage. And in this case, the voltage is 0.46. Of course, it's positive. And what it's saying is, if it's positive like this, it's the copper that is actually the better reductant than the silver. If you want to look at it that way, or you could say the silver is the better oxidant than the copper. Either way, all of this obviously is very much achievable as long as you have a difference in what you would call electrochemical potential between the two reacting species here. You can see that's the case because you get this reaction, and then by splitting it like this, you can actually exploit that electron flow, as I said, and actually use that to do work. Okay, we're then on to the next section.